maybe live without it. But if you guys did, that's great. And if you kind of forget, that's okay too. Um, but I have a sequence for you guys here. And the sequence of numbers, the first value is 1. And the second value is 1 over 10. Third value is 1 over 100, and so on and so forth. And this sequence would just go on forever and ever and ever and ever. Just going to give you guys a second and to have a think. Can you kind of describe a general rule or what the general term of this sequence, a formula, if you will, for getting each of these terms in the sequence? So, for example, you want a formula that when you plug in n equals 1, it gives you 1. When it gives you n equals 2, it gives you 1 over 10. When you plug in n equals 3, it gives you 1 over 100, and so on and so forth. So I'll let you guys have a think. There are some things in common between each of these terms. There's a 1 on top and powers of 10 on the bottom. Perhaps I've said too much. But I'm going to do my attendance while you guys see if you can think of kind of a formula to get the nth term in that sequence. I'll pause my recording. Don't let me forget to restart. Anyone think they have a formula that works? Yeah, Charlie.
1 over 10 to the n minus 1.
Oh, good. Yeah, you even got the n minus 1. Yeah, if you just do 1 over 10 to the n, then that would make the first term 1 over 10. So yeah, great, exactly. And now we can start to introduce this idea of a limit. Now, you guys kind of have already been like informally working with limits. Like you guys, you can correct me if I'm wrong, but like in your first unit last year, you guys did polynomial functions and like talked about, well, if you have like a polynomial function and it's odd degree and leading coefficient is positive, then the end behavior will be like from quadrant 3 to quadrant 1. Does that sound familiar to the language you guys used? Did you guys use any language like this, or did I use it in any of my videos? I don't know. But another way to write that is to say, like, as x approaches infinity, what happens to the y values of this polynomial? Well, for this one, they shoot up towards positive infinity. Do you guys use language like that as well? Perfect. So you guys really, and you could also say, as x approaches minus infinity, the y values approach. So you guys already have some experience with limits. You just really didn't call them limits, so that's good. In this case, if we think about what's happening as n approaches infinity. Now, this isn't saying n equals infinity, because infinity is not like a number that we can just plug in. What happens as n gets really, really, really big? Well, this sequence, can you guys see? Maybe someone who hasn't helped out. What value does this sequence approach as n gets really, 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 really big?
0.
It approaches 0, exactly. So we would say that the limit as n approaches infinity of this discrete function, this sequence Tn, is equal to 0. Now I've thrown in just 2 different notations. Most of the time here in our resource for practice, in my notes, I use the notation where the n approaches infinity is below the limit, LIM. But sometimes just because of a word processing, it's not possible to do that, and you might see it as a subscript instead. They mean the same thing. And in this case, why is this limit expressed as a value that is approached but not reached? Like, will we ever have a term in this sequence that is actually 0? Andrew, you're shaking your head. Why not?
Because like, as the number gets bigger, it's just gonna like the value is just gonna get smaller. It's not gonna get to 0 ever.
It's never going to get to 0. Exactly, because like, you're always going to be doing 1 divided by a number. And even if that number is really, really big, you're never going to get 0. The only way to get 0 with division is if you do 0 divided by something. Yeah, so this is a number we can never get to with our formula. So I will maybe word it this way. In this case, I'll just say there is no value of n, go away, that makes 1 over 10 to the power of n minus 1 equal to 0. We get really close to 0, but we never get to equal to 0. That's okay, because we're just talking about as n approaches infinity, the sequence would approach 0. It never equals to 0, but it gets really, 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 really close to 0. Now let's look at another sequence, 1, 4, 9, 16, 25. This one's not a complicated sequence. It's just squaring the term number. The last sequence approached the value. Those values approach 0. Somebody different, why doesn't this term, this formula, as n gets really, really big, why is there no number we're approaching for this one? So you can think about what the graph of that would look like. Yeah, I mean, I honestly don't have any real better way to put it than that. If you just make a little rough sketch on the side here, and I'm going to do that since I have some space. And you guys know in grade 10, you guys learn what the function y equals x squared looks like. In this one, it's just sequences, so n equals 1, 2, 3. So I'll just plot some points here. But yeah, it's like 1, 1, and then 2, 4, and then 3, 9. And it's just not a parabola that opens up and just shoots off forever and ever, right? So let's just jot that down. So I'm going to say, first of all, I'll try to use a font everybody can see. I'm going to say, in this case, the terms don't approach a specific value. They don't approach a value like 0. They just get bigger and bigger and bigger and don't approach anything. Now, what we can say in these cases, in the previous one, we said that the limit as x approaches infinity of Tn was equal to 0. In this case, I'll give you guys two options here. In this case, we can say the limit as n approaches infinity of Tn. We can say it equals infinity. We understand that infinity is not a number. We're not saying this equals a number. We're saying this to illustrate it shoots off to positive infinity. Are you guys okay with that? Okay. We're not giving your little bro or sis an argument to say, I hate you, infinity. It's not a thing. Or if you prefer, you can say this, and this is kind of familiar to language you used in the 4U functions course. You could say as n approaches infinity, Tn approaches infinity. Those two things mean the same thing. All right, so we've talked about limits as n approaches infinity. And you guys kind of did that with your n behavior for polynomials. Let's start asking questions about as n or as an x value approaches a specific number in a continuous function. So here we have a simple quadratic function. It's the function x squared minus 2. And we're going to investigate what is the limit as x approaches 3 of this continuous function. I wonder if there'll be any surprises in store for us. Who can say? I don't know. If you sit with somebody, maybe they can start at the left-hand side and you can start at the right-hand side, and then we can meet in the middle. Great song by Diamond Rio. I could do the mental math for the first two anyway. Tell you what, I'll start at the right-hand side. I'll do the big ones. So 3.5. No need to show any rough work here. So 10.25. 3.1 squared minus 2. 7.61. Minus 2. I'm just going to go to 2 decimal places. So about 7.06. This one, maybe I lied. I'll go 3. 7.006. I'm going to save 3 for a second. 2.5. Can I do that one in my head? 4.25? Still got it. All right. What's the? Can somebody just rhyme off the next ones for me?
6.01, 6.94, and 6.99.
That's 6.99. Perfect. It looks like as we get close to 3 from the left, and as we get close to 3 from the right, it looks like we're getting close to 7, right? Well, what do we get when we plug in x equals 3? 3 squared minus 2 equals to 7. Do you guys get that as well? Now, if you thought, like, why are we doing this? Like, everything here, there's no surprises, because this is a continuous function. Yeah, we expect the numbers to get close to 7, because that's actually what the y value is when you plug in 3. It is equal to 7. But we're going to introduce some new terminology here, some new notation for you guys. So this notation here is saying, as you approach x from the left, from like the negative side of 3, from the left, the value of this function, x squared minus 2, we showed that they were approaching, as x approaches 3 from that side, our values approached 7. 2, 4.25, 6.41, 6.94, 6.99. Those values got close to 7. And the same thing happened from the right. As you approach 3 from the right, we got values started at 14 and tick down, and they got close to 7 as well. So these two limits have specific names. This first one we call a left-hand limit. Left-hand limit. And then this limit we'll call a right-hand limit. And on the back, on the next page, I just have a graph of this function. And as I said, there's absolutely no surprises here. When x equals 3 on this graph, y is equal to 7. We can see the 0.37 right there. And I would say it does make sense to say the limit as x approaches 3 of x squared minus 2 exists. It looks like it's equal to 7. We confirmed it numerically. You guys can see on the graph. Think about just like if you were a tiny ant and you were like surfing on the graph. As you got close to 3 from each side, the y values are approaching 7. You guys convinced this limit exists? It equals to 7. But again, no surprises here. It's just a nice continuous function. Nothing weird is going on. We're just introducing some new notation. So the left-hand limit was 7. The right-hand limit was 7. The limit overall as x approaches 3 here was equal to 7. So just to summarize, in general, a limit exists if, and I'm going to put this in words, and then we'll actually state the formal conditions for a limit to exist just in terms of math here. I think this font size is good enough. If, just in general, the values approach the same specific number from both the left and the right, which they did here. From the left, our y values approach 7. From the right, our y values approach 7. Formally, we are going to say that the limit as x approaches a for some function exists if these 3 criteria are met. We're just going to basically turn this general idea of a limit existing into math. So here are the 3 criteria. Now you might wonder for the third one why it's needed, and I'll show you guys an example of why. But the first condition is this. The first condition for a limit to exist is that the left-hand limit has to exist. So the limit as x approaches a from the negative side of f of x exists. The left-hand limit exists. And the second condition is that the limit as x approaches a from the positive side of f of x also exists. I'm going to draw a function where those two things are true, but the limit doesn't exist to illustrate why we need this third one. So you guys can jot this down too. I'm just going to make a axis here. And I don't even need to like make a scale or anything. So I'm going to have a point here and just start a function that maybe looks like that. Like you guys know, like the radical function, maybe that's just like a radical function just shifted right and up. And then to the left of that, I'm going to define the function to look like the following. So I'm going to have an open dot down below, and then I'll have my function just looking like this. So this is called a piecewise defined function. You can imagine it's like a light switch. Like the function looks like this, and then at some specific time, a switch is flipped, and now the function is different. It's no different than like turning on the lights in a room or turning on a device. Things can instantaneously change like that. Now this is the function. If you guys were to go back into grade 11 math and do your vertical line test, this function would pass a vertical line test. It is a function, but the left-hand limit approaches one number. The right-hand limit approaches a different number. It wouldn't make sense to say that the limit as x approaches whatever this value is exists. We need a third condition. Not only do these two things have to exist, they have to equal the same number. So the left-hand limit has to equal the right-hand limit. That's the third condition. The limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right. Left-hand limit equals right-hand limit. And for any continuous function, like a polynomial function, you're never going to run into this issue. The limit will always exist. And just to illustrate that, I've graphed here. I didn't graph it. I stole this graph. I stole this graph from the textbook. Here's a function. It doesn't matter what the equation of this function is. Here's its graph. And from this graph, I'm asking you guys, what's the left-hand limit as x approaches 4? What is the right-hand limit as x approaches 4? Can you make a conclusion about what the limit as x approaches 4 is? And then what is the value of the function at 4? Well, let you guys have a think on this. Little hint, don't think overly hard about this. Sometimes it's helpful to pretend you're really, really, really small, like you're in Honey, I Shrunk the Kids, and you're just like surfing along the curve and you're approaching this value from the left and right. Some brave soul want to volunteer the left-hand limit, possibly somebody who hasn't helped out yet today. As we approach 4 from the left, Charlie. -2. Somebody different. How about when we approach 4 from the right? I'm looking over there because nobody's helped out yet. Yeah. Also -2. Left-hand limit exists. Right-hand limit exists. They are the same value. So I got C for you guys. The limit as x approaches 4 is -2. And the y value, f at 4, is also equal to -2. Absolutely no surprises. I'm even going to write that down. No surprises. This is a continuous function. Continuous polynomial function. Nothing weird happened. All right, we're going to start talking about some weirder stuff though. But yeah, with a continuous function, like any polynomial, this is always going to happen. The limit exists, the limit's just going to be the y value. It's just a continuous function. Let's look at a different function. Now you guys have seen this function before. It's the radical function. We're going to ask ourselves, what's the limit as x approaches 0 of this radical function? Now, I'm going to draw just off to the left what this function looks like. You guys can do it with me. You guys should know what this function looks like. Starts at 0, 0. And it's essentially like half a parabola just tipped on its side, something like that. F of x equals root x. Now, I'm going to ask you guys kind of the same questions as before. For that function, now that we have the graph, what's the left-hand limit? What's the right-hand limit? If they exist, and if they both exist from the same value, what's the value of the limit? Now, actually, I've given you guys a bit of a clue. This limit does not exist. So something here in our three conditions has to break down. So maybe you guys can have a think about which of those three kind of break down here. I'll give you guys a think. I'll have a sip of coffee, and then we'll chat together. Let's pretend you were shrunk down and this function was actually something physical you could slide down. Would you guys agree, as you approach 0 from the right, the y values approach 0 as well, right? You could physically surf down that curve from the right. The right-hand limit here, in this case, the limit as x approaches 0 from the right of root x exists and equals to 0. Did anyone already see the problem with what's the problem here? Kara? There's no left-hand limit because the domain of the square root function from your grade 11 course, you can only square root numbers that are non-negative, right? 0 or positive. There's no function for us to surf along the function and see what happens when x approaches 0 from the left. The function doesn't exist there. The limit as x approaches 0 from the left of root x, I'm just going to say DNE for does not exist, just because I'm a little lazy, just to save us some writing there. It doesn't exist. I'll just kind of finish this up. Therefore, the limit as x approaches approaches 0 of root x does not exist. It's because that left-hand limit doesn't exist. So this is our first example of a limit not existing for kind of a function we kind of have in our repertoire, and it's because the domain of this function is restricted. The function starts at 0. The left-hand limit doesn't exist. If I could tease just the tiniest little bit, a few days from now, I'm not going to give away too much. You guys know how we've been finding instantaneous rate of change, right? Slopes of tangent lines. If I asked you guys to find the slope of the tangent line at 0, what would that look like for this function? Well, we know a tangent line touches the curve at just one spot, right? Like that would be the tangent line for there. But at 0, 0, well, the function stops. So I could draw a whole bunch of lines that touch that point exactly once. Which one's a tangent line? It's actually like impossible to say. So it kind of makes sense. It will make sense a bit later why we got this limit doesn't exist. Okay, don't want to tease too much. Let's continue. I have another interesting scenario for you guys here. And I think we might actually just wrap it up with this example. We'll see time-wise. I'm not used to the time crunch in this class. We get like so little time compared to like previous years. What did you guys have period 1 last year? Did you have it like an important class? Okay, class starts at 8:40. Please try to be here. All right, let's continue. So here's another function, x squared minus 1 over x minus 1. This is a rational function, which you guys would have worked with in, sorry, I'm distracted. I'm just teaching, which is why I asked you guys to be here. You need the lesson sheet, right? So we're going to look at the limit as x approaches 1 for this rational function. Again, I'm asking you guys to slam in a few values as x approaches 1 from the left and the right, and to see if we can kind of reason out what the limit might be as x approaches 1 for this function. So again, maybe I'll take the right-hand ones. You guys can take the left-hand ones. It's possible you've already got many of these done. Divided by 0.5. So that one's 2.5. 1.1 squared minus 1. This one's 2.1. And this one's 2.01. I'm going to guess this one would be then 1.5. Is it symmetrical like that? 1.9, 1.99? Okay, perfect. All right, so can you guys have a think? I'll wait 30 seconds. As we approach 1 from the left-hand limit, or does it look like we're approaching some value? As we approach x equals 1 from the right, does it look like we're approaching some value? If the answer is yes, and they're the same, then possibly this limit exists. Does it look like they're all approaching the same value? It looks like we approach 2 from the left, 1.5, 1.9, 1.91, and we do actually. So as we approach 1, not as when x equals 1, but as we get really, really close to 1, those values are getting really, really close to 2. And the same thing happens from the right. And if the left-hand limit and the right-hand limit exist and equal to each other, then the limit as x approaches 1 exists too. But does f at 1 actually exist? What do you guys get when you plug in 1? You get 0 over 0, which is not good. So f at 1, 0 squared minus 1 over 0, f at 1. I'm plugging in f at 0. 1 squared minus 1 over 1 minus 1. This is not good. 0 over 0. Some smart alecky grade 9s might be like, well, 0 over 0 is 1. Anything divided by itself is 1. But no, it's not 1. This is indeterminate form, 0 over 0. It's undefined. This is undefined. So this is an interesting case. Unlike that polynomial one, here the limit exists, but there's actually no y value at that function. So what's going on here? What does this graph look like? Now, you guys did graphs like this last year, so we'll graph this one together. What you guys would have done with Miss Houston is you would have, you'd be in the habit of trying to factor everything as much as you can. And you guys would see the top is the difference of squares, x plus 1, x minus 1. And that the x minus 1s divide out. And you're left with this function is actually equivalent to just the linear function x plus 1, except it's almost equivalent to it, except at one specific value, x equals 1, because then you get 0 over 0. And what this graph would look like, it just looks like the line x plus 1, y-intercept of 1, and a slope of 1, except at x equals 1, there's a hole in the graph, kind of like this. So this is what the graph of our function f of x would look like. It's just a linear function with a hole in it at the point 1, 2. As we surf along this curve and we approach 1 from the left, again, we're approaching 1. We're not saying what happens when x equals 1. As you approach 1 from the left, the y values approach 2. As you approach 1 from the right, the y values approach 2. So the limit was equal to 2, but the function doesn't exist, and that's okay. If I don't want to steal too much again, but if you guys think back to the difference quotients you guys have been doing, if you go back to your difference quotients and you start at the very beginning and you just plug in h equals 0, you get 0 over 0. But instead of asking what happens when h equals 0, if we ask, well, what happens as h gets really, really close to 0, well, that's a different story. It's like this one. We can't plug in 1 because we get something undefined, but we can ask what happens when x gets close to 1. The y values get close to 2. We're really, really, really close to being able to go back and find instantaneous rates of change directly. We're almost. I think I might do one from the back here. I want to give you guys time in class, and our time is kind of short. So this function here is an example of a function that had a discontinuity, and it was a hole here where the function wasn't defined. A few lessons down the road, I give you guys a formal definition of what it means for a function to be continuous. But for now, you guys can just jot this down. It is possible, a limit can exist at a point, even if the function is not continuous. I can spell at that point. So hopefully you're convinced with the example we just did. Limit can exist even if the function isn't defined at a point or not continuous there. All right, so what does it mean for a function to be continuous at a point? I'm going to give you guys the first two conditions and then give you an example about why we need a third one. So first of all, a function is continuous at some number if, first of all, if f at a is actually defined. So f at a is defined. So basically, there's like a point there. The function exists there. And it's continuous if the limit as x approaches a of f at a exists. And then I'm going to give you guys, like the last time, I'm going to give you guys a graph where those two conditions are satisfied, but the limit doesn't exist. So check this out. I'm just going to draw some function here with a hole in it, and then I'll just have it continue. So this function, as it stands right now, has a hole at x equals a, but I'm just going to make I'm just going to define the function to be some point above like that at x equals a. So this is a function. It passes a vertical line test. F at a is defined. When x is a, the y value is up here. And the limit exists too. As you approach this value of a from the right, we approach this y value where the hole is, from the left, excuse me. Same thing from the right. But in this case, those two things don't line up. So the third condition for a function to be continuous is that the limit as x approaches a of f at a has to equal, I should say f at x, has to equal the value of the function. This happened in our examples with the polynomials. This is always true with continuous polynomial functions. It's not always true when you come up with funky functions like I drew there. Okay, I think actually I want to get you guys time to practice. So the stuff on the back here is not terribly important. You can look at it if you'd like to and think about what those values approach. But I'd just rather get you guys practicing. I'll give you guys hard copies as well. But before I dish those out, is there anything you guys want to chat about?
Well, with that third condition,
Yep.
for the graph we just did previously,
Yep.
f at a would be undefined, but the limit is 2.
So the one we did before?
Yeah.
Right, so this function is not continuous at x equals 1. Yeah, this one is not continuous. This function is continuous everywhere else. Everywhere else, the values are defined, and the limit would equal that value, except here, there's no value. All right, so you can wave me off. I'm going to stop recording. You can wave me off if you're